Thank you everyone for coming. So Varna asked me if I wanted to organize something. I have a year off from teaching, so I think Ian, Chris, and Fasil, and Vincent. Vincent said, I don't want to fly. I want to be with my family. Okay, cool. But yeah, we have his blessings to do clustering. And nowadays, yeah, he's the clustering guy, so we need some authority saying, okay, you can do clustering now. So yeah, so the first speaker is Samir, and he's going to tell us about old questions. I have a bias towards old questions because I think we should solve them before new questions start. So I'm very happy that you're speaking.
Thank you so much. Yeah. Thank you so much for organizing this workshop and for asking me to speak. I haven't actually done that much work in clustering in 10 years, so it's like replanting, still waking up and seeing what's been happening in the world. So I just thought I'll attempt to find out what's been happening, but then they asked me to speak, so I thought I'd talk a little bit about some old favorite problems on case-center clustering. I know the world is slowly polarizing, but after this workshop, we just say the world is clustering. Okay, so let me go ahead and get started. So when I tried to do a full screen slide share, it was putting up 2 slides at a time, so that didn't look that good. So I just thought I'll walk through the slides one by one. So I'm going to talk about 2 sort of central versions in clustering. Many of you are familiar with these, but just to recap some definitions. So first problem is case-center clustering. Just given a graph G, I want to pick K nodes. Think of them as facilities, and then I simply care about the maximum distance that any client has to travel to a chosen center. So in this model, K is fixed, and the objective is to minimize the furthest distance some client might need to travel. And of course, the client goes to the closest center. So here, there's no capacity notion, unbounded number of clients can go to the same facility. And then there's another popular model of clustering called K-suppliers. Those of you who work in facility location, this might look more familiar. So here we have a bipartite graph with X and Y. And from the X set, I want to pick a subset of facilities. And then I care about the service cost for only the clients, not for the nodes in X. So again, we do the same measurement of the distance that every client in Y has to travel to get to its closest facility. So as you know, both of these problems were shown to be NP-hard a long time ago. And in metrics, there are optimal guarantees, optimal factor 2 approximation for the K-center problem and optimal factor 3 approximation for the K-supplier problem. So one interesting question is what happens? Is this size font big enough to read? Actually, I wasn't sure. I wrote these last night on my iPad and I realized I should have made them bigger. But what about Euclidean distances or points in 2D or in RD? Other interesting generalizations that we used to think about a long time ago have to do when nodes have associated costs, similar to facility location. But a lot of these things actually happened before facility location became popular. So the idea is I give you a budget of K dollars to spend, every node has some cost. So rather than opening at exactly K centers, we have a budget that we want to spend. It's also known as the knapsack center problem. The other interesting version is called the outlier version that I know many of you have worked on, where there's a small number of outliers that we don't care about the cost to connect them, and then we have to focus on providing high quality service to say 90% or 95% of the clients, right? So, but we don't know which percentage of the clients will be left with outliers. And then finally, I'll talk a little bit about the notion of capacities when centers have capacities. And feel free to stop me anytime if you have questions. So I take you back to 1988, long time ago. So this Euclidean K-center problem was studied by Feder and Green, 1988 paper, where they were trying to develop hardness results for the geometric K-center problem. And the part of the paper that I remember is the K-center hardness of something around 1.82 approximation. In later work, people cited their bound of square root 7 for K-supplier hardness. I don't recall whether it was in the stock paper or not in 88, but for sure, I think their techniques can be used to derive that bound if it wasn't actually explicitly laid out. And these are all very classical reductions. So they just assume that planar vertex cover in degree 3 graphs is NP-hard, and then basically proceed to take an embedding of the planar graph, and then essentially convert that to a point set in the Euclidean plane, and then say, well, if the graph had a vertex cover of some size, I give you a budget on how many centers you can choose, and then if one edge of the graph was left uncovered, then some client is sort of far away from the center. Intuitively, it's a technically hairy construction because you have to go through a lot of tedious details, but conceptually it's very simple. It's classical. It's not really using anything with PCPs and so on. Right? But that still left open a couple of interesting questions. One is simply in K-center, can we still beat 2? Because the lower bound that they showed was something like 1.82, and in K-suppliers, can we get better than 3? Okay. So as far as I know, the first question is still open, and maybe some of you have thought about this and maybe have some updates on us in this workshop. But there's a very elegant result that I wanted to describe for the K suppliers problem that beats 3 for the Euclidean case. How many people have seen that result before? I don't know how much. Okay, so there's at least a good fraction of people who don't know that. So it's something to talk about because I think it's a very, very interesting idea. This is a paper by Nagarajan, Park Shaper, and Natash Shaknai. And so their bound is not bad. It's 1 plus square root of 3, which is 2.732, which is only a little bit more than square root 7. So I think it's a great bound. Their algorithm is also very simple, and I'll proceed to explain the algorithm in a few minutes. But here's the entire algorithm that is in the page 2 of the paper. Okay? So it says you guess the value of opt, and this is a very standard trick in case center problems where we know the optimum is some distance between some client and some center. So you can kind of do some, if you don't worry about running time too much, you can do an enumeration of guessing the opt. And then in the standard Hopcom-Schmois type approach, you find a maximal independent set in some associated threshold graph. And they're sort of following a similar approach here. So they say that let P be a maximal subset of clients whose pairwise distance is at least as big as square root of 3 times opt. So this is where the geometry is going to come in. And then they construct a graph on those clients. And then they add an edge between a pair of chosen clients in that maximal set P, such that both have the property that there's a supplier with an opt distance from that client. Okay, so that's roughly the construction. So there's certain associated graph being built after I've chosen this maximal independent set, and then finally they compute a minimum edge cover in this graph, which can be done by meshes. Right, so it gives you a very clean, succinct polynomial time algorithm. So let me explain sort of a little bit about what's happening intuitively. So what's the conceptual idea? The conceptual idea goes back to an old paper by Hopcom-Schmois in the mid-80s, where the idea is sort of the following. Imagine the optimum clustering, it looks like this. And if I pick any vertex V, and I say, what if I decide to open a center here, right? We don't know which is the optimum center that covers this V, but if I mark everybody within radius 2r as being covered, then for sure we will cover the entire cluster. And no other vertex will be left uncovered in that cluster, and we can keep going greedily. If I end up picking too many nodes in this way, then our guess for the radius was too low, and you have to revise the guess. If I pick at most k and I've covered everybody in 2r, I'm done. So the smallest radius value for which you're successful, you basically stop it. Okay? So that was their idea. So that idea can also be applied to K suppliers. But why do you get the factor of 3? So in K suppliers, remember there's a bipartite graph model with two sets X and Y. If I focus on an uncovered client V that I want to cover, V is covered by some optimal facility in set X. We don't know what that is. And so maybe we are thinking of picking that node to cover V, but in fact, maybe optimum to pick some other node. So if I want to make sure that by the choice that we make, we have to pick a facility on the left, we can't pick a node on the right, then we might have to travel 3 hops in this undirected graph to be able to cover everything that node would have covered. Okay. Any questions about that? So that's sort of where the factor 3 comes from in this part. Right, because it's the bipartite construction. And then also leads to the hardness from set cover. So what's going on in the Euclidean case? So in the Euclidean case, something interesting is going on. So when I pick this vertex V, and I'm going to choose some supplier to cover vertex V within radius r, we could cover everybody within radius 2r, and that will give us back to the factor 3. But instead, they are lowering the covering radius slightly to square root of 3r, which is less than 2. And so they mark everything within root 3r as being covered, right? And so that might leave a few nodes in this same center as uncovered right now, right? But notice that the moment I pick a second node there, I will also cover everybody within square root of 3r. And they're using geometric property that says within this ball, once I pick 2 nodes of radius root 3r, then everybody in the ball is covered. And that's where the geometry comes into. Okay, so that's sort of the central idea in their algorithm. So you'll keep going, you pick pairs of vertices that are sort of far apart from each other, where far is defined as square root 3r. But within every cluster, at most 2 nodes can be chosen. And so if you still end up picking more than 2k nodes, you sort of say, think failed, the radius was too small, try again. If I pick at most k, I kind of can stop and I'm done quite well. But where does the edge cover come in? The edge cover comes in to say that these 2 nodes that we ended up choosing in the same cluster, where did the picture go? These 2 nodes that I ended up picking. Oh, where did I do this slide? I thought there was one more slide. Yeah, this one. So these two nodes that I end up picking in the same cluster, notice that they do have an optimum facility, which is within R of both of them. So that's why those two for sure, when they get chosen from the same cluster, will have an edge between them. And then we find the edge cover. And edge cover is simply the smallest number of edges to cover all of the nodes in the graph. And also self loops are allowed here, because you might have some isolated client that needs to be closed. Okay. So that's sort of the central idea in their algorithm. So it's a very, very clean algorithm. So they basically have two main theorems in the paper. One is that using matching, you can get this bound of 1 plus square root of 3. The addition of 1 comes in the cost of shifting from the client to a facility within distance R, and that's in polynomial time due to matchings. But then they show that if you didn't, so you just wanted to beat 3, then you can get something slightly better than 3 much faster, like in close to linear time. I think it was like n log n or n log square. So again, they're not using exact matchings there, they're using approximations. So let me keep track of time. So other generalizations, yeah.
The 3 minus epsilon is also using the
Same approach, but they are sort of using approximate nearest neighbor data structures and a bunch of things and approximate matchings. So I'm not sure whether or not you can get like square root 3 plus epsilon, but there is a gap there. It's bound to something like 2.9 something. Some of those who are familiar with the paper might remember exactly what trick they used. Department might be. You raised your hand earlier about square root 3. Okay. So what about other generalizations? So I know sometimes you study these problems, like I've been thinking about this a long time ago. Some versions became extremely popular and other versions somehow didn't. So here's a version that did not become that popular, which is case center with capacities. I know facility location with capacities became very popular, but not case center with capacities. So here the idea is very similar to the standard case center problem. I want to pick k nodes, but now every vertex that is not chosen has to be connected to some assigned center. And I simply want to minimize the maximum distance of a node to an assigned center. But now, in the model that we studied a long time ago, we assumed uniform capacities in every open center of L. So at most, L clients can be connected to an open center. So here, basically, we were able to show two things. If a vertex can be selected multiple times, so namely that if I put a facility down at node 1, maybe some L clients can connect to it, but I can open a facility at the same vertex node 2, then L additional clients can be connected to it. So for that version, we can get a 5 approximation. And again, this is only using metrics. It's not using geometry at all. And so a problem I did think about back then was how can we use geometry to improve the bound of 5, and they haven't been able to do it. But again, I think this is the place where a lot of improvements can be done because the bound is quite high, it's 5. But if a node can only be selected once due to some technical shifting issues, the bound we got was 6. And again, I think an interesting question is, are they better lower bounds for the version with capacities? So again, I suspect that the right answer could be something like a factor 3 approximation maybe. So maybe with capacities 3 is possibly, let me go be as bold to conjecture that 3 is the right answer. And what was the sort of central idea behind this algorithm? The central idea was very simple. It was motivated by the Hopcomb-Schmoyes threshold graph approach. But the idea was that we will do a breadth first search exploration in this threshold graph. So recall the threshold graph is simply a undirected unweighted graph where edges are added within pairs of nodes with distance at most R, which is our optimum guess. And we basically run a breadth first search. So I pick a vertex as a root. So that's sort of a special node. And then I mark everybody within distance 2 as being covered. And then we sort of go to a neighbor of a covered node and then pick that as a center. So in some sense, we are being a little bit careful about the choice of centers here. We're not just picking centers arbitrarily. We're basically doing this BFS exploration. So you can think of this as level 0, level 1, level 2. And as soon as I reach a level 3 node, I will choose that as a center, then mark everybody within distance 2 covered and so on. So just the choice of centers is being done a little bit carefully. And then we basically build such a tree in every connected component. And intuitively, what's happening is, of course, the algorithm is some bells and whistles. They have some network flow going on and trying to figure out a way to assign things and all that because of the capacity issues. But fundamentally, after an initial phase of assignment, the intuitive idea is that a node might not have enough capacity to handle everybody close to it, and it's just going to pass the excess up to its parent. Okay? And when you pass the excess up to the parent is going to then give priority to any passed up clients that are coming up from its children, assign those first, and then pass things back up. And eventually, sort of everything is resolved at the root, and sort of the root intuitively could be one of the few nodes left in this construction with number of clients assigned to it less than the capacity, and you have to sort of account for that. But intuitively, the central idea of this algorithm is simply being very careful in the choice of centers and making sure that every center, except for the root that is chosen, has somehow this parent that it can pass things on to. And so the way the factor 5 is coming from is that your parent is kind of 3 hops away and then clients being assigned to your distance 2. So that's exactly where the 5 comes from. Because you might have to travel 5 edges to get anything to be assigned in this algorithm. Now, this tree construction is actually quite useful. So, for example, there was a paper, I remember Ola Svensson was one of the authors, and maybe some of the authors are in the room. It was like 6 or 7 author paper in maybe IPCO a few years ago, which looked at non-uniform capacities on the facility. So you have again a graph, but the capacities are not uniform. Every node has some capacity function. And in the non-uniform capacity, it's a little bit more complicated construction because you first have to solve an LP, but then they use the same tree construction in rounding the solution.
How do you argue that routing just along the tree does not incur like a big additional cost? Like, you may imagine that you're looking only at routing through a spanning subgraph instead of routing through the whole graph, and in principle, it feels like routing outside of the tree may be much cheaper than just within.
You're absolutely right, and that's why I said I think the right answer is 3. So the 5 is really an artifact of this construction because as you're running this BFS very carefully and picking nodes at levels, there are other edges that you're absolutely right, they're not using at all. And so it's possible that some node that thinks there's a client, there's a server here that it wants to connect to, or a facility here it wants to connect to. Right now, that facility is only going to pass it on to its parent, which is 3 edges away. But maybe in the graph, there are other ways of optimizing it. That's why I don't think about 5 is the right answer.
I mean, doesn't it accumulate that you have to pass there?
No, we only pass one level. So what happens is that the whole processing happens bottom up. So if you have a very large number of clients near you, you can keep opening multiple facilities, right? Because of the assumption that I can open multiple facilities. So let's say you tell me there's 3.5 L clients here. I'll say, okay, go ahead and open 3 centers because I can justify them, they are fully loaded. And then the remaining half L customers are what will pass up one level. And then every node first waits to see what it should pass up, gives them priority, handles them, and then passes things.
The multiplicity of facilities is what was saying.
And when you don't have the multiplicity model, then it gets a little bit more technical because in this tree, we sort of imagine that we piled up centers on top of each other. Now we have to shift them and move them around. And then again, if you're not very careful, you can show that shifting by 2 hops is easy, but shifting by 1 hop is actually where the challenge came, and that's where the 6 came from. So getting 7 from the 5 is trivial, and then 6 is more. But again, these are a lot of nasty details, like 2-3 pages of case analysis basically. But the nice thing about the tree construction is that it was quite useful. So for example, in this factor 9 LP rounding algorithm, you can just solve the LP, use the same tree, and then they're basically doing a rounding of the LP, but the tree is sort of the guide, right? And again, my open question is maybe we can do better with Euclidean methods. So let's talk a little bit about outliers. So what motivated outliers? So the k-center model, as we know, is very strong model, right? Because we're measuring the distance of every client to its closest center, and then we're taking the max. So there could be, clustering instances where the right answer is that these are the 3 clusters, and maybe we shouldn't even worry about a few people who decide to live far away, and maybe service to them is going to be very, very expensive, right? So either you can open more clusters, or if you try to encompass everybody, then the radius should go up, right? So the idea was that you wanted to ignore some number of outliers. So the goal was, again, Z is somehow a budget on outliers, so I want to make sure I cover n prime points. And make sure that the cardinality of the vertices that get covered is quite high. And again, I want to minimize the maximum radius. So 95% is headers, we can replace that by anything you want. So what happens in the study of clustering with outliers? So in an old paper with Moses, Charikar, Dave Mount, and Giri Narasimhan, we showed a very simple greedy approximation that gives you a factor 3 for k-center. And also, I don't remember the exact bounds, either 3 or 4 for facility location as well. Now, these bounds can be improved to 2 by linear programs. And I don't know whether the department in this talk will mention some of the results of that, but they studied a more general problem actually here, of which the outlier version turns out to be a special case, and they get an LP rounding algorithm gives 2. And Marek and myself were also actually had that same algorithm that they have in their paper, but we were trying to do something with outliers and capacities at the same time. So at that time, we weren't successful. We were only able to get the factor 2 using LPs. But later on, Marek with his PhD in Kochimaka, I think that's how you pronounce it, Kochimaka, they had a paper which gave an order 1 approximation for exactly that problem, where you have non-uniform capacities and outliers. Again, you can ask the same question: what happens in the K median problem? So Chen had shown already that order 1 approximation, but the constant was kind of high for K median with outliers. And then now, most recently, just last night, I was searching, I found a paper by Krishnaswamy, Shidi, and Sandeep, which gives a bound of roughly around 7 based on rounding for K median with outliers. So that's quite interesting. I never thought the bound would be down to 7. Let's see. How much time do you have?
10 minutes.
Okay, so maybe let me say a few words about this algorithm, because this algorithm is actually a little bit surprising. It was almost a bet that Giri and I had. Giri's conjecture was that no greedy algorithm would work. But then here's a greedy algorithm that does work. So here, again, we are working with a threshold graph after guessing the radius R. And the whole idea is to simply pick cluster centers that are dense. So intuitively, we define for every vertex its neighborhood, which is the cardinality of the number of nodes sort of close to it. And then we greedily want to pick based on this measure. Because if I want to be able to cover 95% points, we want to intuitively open centers that can cover lots of vertices, right? And the key trick is that even though we pick based on this small radius R, definition of NV is based on this radius R, but we still mark out all points within radius 3R. Now, actually, the algorithm fails. You could have said, maybe if I'm going to cover everybody within 3R, why don't I greedily just pick whoever has the largest number of people within a radius of 3R? That algorithm actually fails. So, kind of this choice of R being used as one measure and 3R as the covering measure is critical in the proof. And here's the intuition as to why the algorithm works. If you imagine the optimum solution as a collection of K clusters, each cluster covers some number of points, so N1, N2, N3, and so on. And we want to make sure that in our choice of K centers, we're also covering at least as many points as we are. If we undershoot, then we start getting a bi-criteria bound. The challenge that happens when you pick a greedy choice, this center might start damaging some of these clusters. So in the first step, I can claim that I will cover at least N1 points, but that statement will not stay true as we continue. So we want to make sure that if I damage a cluster, damaging means that it will have fewer points after some nodes have been covered, then we want to make sure the whole cluster is covered, right? That's why we have to expand here. So the LP rounding is using a completely different approach. So let me say maybe an open problem here for the outlier version when nodes have costs.
Samir, there's a question.
Yeah, sorry.
There's a question in the chat.
Oh, the chat.
What does U in UNC mean?
Say it again.
U in UNC, what does the
Oh.
letter U?
So U is any vertex. And so this is the cardinality of all nodes U, so the distance from U to V is at most R, and U is uncovered. Oh, UNC. Okay. Not University of North Carolina. Uncovered.
You explained all the U's.
Okay. So what's the situation in the outlier version with cost? So again, remember the cost version is that nodes have cost. You have a budget of K, you have to make sure that you stay within the budget, and you want to open centers within the budget, but you also now have to cover like this desired number of points, 95% to 93%. So in the outlier version, yeah, so factor 3 is quite easy in the non-outlier version, but the outlier version, the setting is open as well. Okay. Question? Is there anything wrong with clusters of capacities and outliers that are allowed? Yes, so that's the Kochimaka-Sigan paper. And in fact, it handles non-uniform capacities as well. So again, I think that's an interesting problem. This outlier version paper, which approximately meets the budget, I'm trying to remember all the authors. I know my former student Jian Li was a co-author, but I don't remember everybody he worked with on that. There were 4 authors, and it probably appeared in it like 2010. So remarks. So when I first learned about K centers, I came across 2 different algorithms. One was the Hopcom-Schmalz 85 paper, and one was a paper by Gonzalez, which has this different idea, which basically says, take your entire space, there's no thresholding, just plonk the first center down anywhere, then go to the node that is the unhappiest in a way, put the next center there, put the next center there, and keep going, and whenever you don't have centers, you stop. The beauty about this algorithm is that it's completely incremental. So if you want to build like additional facilities or hospitals as time goes on, this tells you that you can basically in advance give a permutation of all the nodes in the graph, And then just keep opening centers incrementally, and for whenever you stop, you are too competitive, right? So that's kind of interesting property about this algorithm, but all of these generalizations that you see, we haven't really made use of this incremental property. So I know for K-median, Metu and Plaxton had a paper a long time ago, where they basically showed similar kind of results for K-median, which are like an incremental algorithm, right? So again, I'm sure Metu Plaxton's work was improved over time, but it was a very impressive result when I saw it because they also got something similar for K-median. I don't know whether anybody's looked at K-means. The other comment I wanted to make was about the streaming setting. So again, the streaming setting is kind of interesting because the data itself is coming to you incrementally. You have very limited memory, you can only hold K points, and you will at all times maintain some kind of lower bound of R. So whenever a new point arrives, you basically say either it is close to some stored point, I can only remember K things. If it is close to it, I just throw it away. If it is very far from it, now I have sort of K plus 1 points intuitively far apart. This will trigger a new algorithm that will be run offline on these K plus 1 points, allow you to increase your lower bound of the radius. And this also gives you like a constant approximation to K center. The beauty is that whenever the stream stops, you're just remembering K points, and that's what you output as your representation of your cluster. And every forgotten point is close to at least one of these. Right? So I think it's a very, very cool idea, kind of intuitively surprising that it can be done, but I thought it was really nice, right? So it's a very useful way of clustering. And so if you're thinking about like applications, so I have a pardon?
What approximation do you get for the
So in the deterministic bound, it's something like 8. And then in the randomized version, actually this is Moses Charikar's paper. This is one of the authors. I think it's something like 2E. Yeah. But it's a very, very nice algorithm. Again, the bound might have been improved, but I thought both the algorithm and so on was very beautiful. So I was talking to a computational biologist one time, and he was having the following challenge. So he had a bunch of things that he wanted to cluster. Each thing, think of it as a very long string. But now trying to figure out the distance between two strings is a very expensive operation. They have to basically run a dynamic program, some kind of edit distance. And so he was complaining to me that his data is so big that he cannot even just compute pairs between all the pairs of points, and that's very expensive. So then I told him about the streaming algorithm, because the streaming algorithm, whenever a new point arrives, only basically computes its distance with the K things that you stored. It doesn't care about anything else. And so later on, he told me that that was a very useful suggestion, and he was actually able to speed up his clustering scheme in his computational biology project significantly. So to me, that was kind of exciting to hear that some central theory ideas, which are very simple and very elegant, were able to actually play this valuable role in computational biology. So again, to conclude, geometric K center still needs new ideas. I think they're kind of stuck there. I have one idea that I've thought about on and off, but I'm happy to chat with anybody interested, but I don't sort of know how to convert it to a full algorithm. Again, by robust, I mean the outlier version needs new ideas. Again, there's no sort of pure bound known, which will give you factor 3 approximation. It relaxes the budget. Topic that has become very popular lately is fair clustering. I didn't have time to talk about it, but I do think that these results in the streaming setting are super interesting, and many clustering problems should be looked at in the streaming setting. Okay, so let me stop here. These are all pictures from San Diego, by the way. La Jolla. So in case you have time in the next weeks.
Any question? Yeah, a minute.
Yeah.
And what would you say for the supplier problem? If we allow the capacities to be slightly exceeded, like
Oh, then you can do much better. So in the paper I had with Yoram Sussman, we looked at both K center and K supplier. And if I remember correctly, if you're allowed to violate capacities for both those problems, you can get very good bounds. Yeah, it's only when the capacity bound is hard that it's challenging. But if you're allowed to violate the capacity bound slightly, you can do quite well. In fact, we showed some kind of trade-off maybe between number of centers and capacities. Yeah.
You mentioned 2D.
Yes.
And I guess you said we were sort of extract with the factor 2 in 2D. So I wanted to ask you, but do you think it's going to extend to 3D? But I guess
No, that's a very good question. 3D. So if I think about the Nagarajan, Shibar, Chaknai result, I think that geometric property works for 3Ds also, right? Basically, if you have the sphere, I can't think very high dimensions, but sphere, I think you can still easily prove that if you pick one point and that you cover everybody in the distance square root 3r, whatever is left, you pick one more point uncovered within the same ball, it will cover everything. So for 3D for sure, that same algorithm basically works. I don't know whether it works for every dimension. Oh, any Euclidean.
3 points.
Are needed.
I see. So even high dimension.
Yeah,
Nice.
yeah. So it's a very powerful idea, but yeah, it was somehow escaping most people who thought about case suppliers. But the ancient came a very clean algorithm.
Thanks.
Thank the speaker.